Okay, so this video will have an example of using the momentum integral boundary layer equation that was derived in another video, and how to take an approximate velocity profile and utilize it to then determine things like the boundary layer thickness as a function of x and the wall shear stress as a function of x. So let's say we have a laminar boundary layer that can be approximated with this profile. So we just have purely linear. The equation is just that the velocity divided by its upstream value is just the y location divided by the thickness at that location. And then outside of this boundary layer, we just have unity. I guess this is saying that the velocity is just a free stream value. All right, so our momentum integral boundary layer equation is given here, which relates the wall shear stress to the change in the length change in the boundary layer height. So it's a change in the boundary layer height with length in the x direction. And then we also have that shear stress, the wall shear stress can be related to the gradient of the velocity at the wall. So here we can just take our equation for our velocity profile and just divide it and evaluate it at y equals 0, and we find that the wall shear stress is just viscosity times the free stream velocity over the boundary layer thickness. We then go over here to this relationship. We can then determine what our boundary layer momentum thickness is by plugging in our velocity profile. Right, so this is a definition, which for our case, u is just, u over big U is just y over delta, so we can replace that. And this goes to 0 everywhere outside of delta, right? Because 1 minus u over big U is just 1 outside of y, for y is greater than delta. So we can just evaluate the integral from 0 to delta, plugging in what u over big U is just y over delta. We plug that in and take the integral. We get a y squared term and a y cubed term. Evaluate it from 0 to our boundary layer thickness. We just get delta times 1/2 minus 1/3, which gives us 1/6. So that says that our boundary layer momentum thickness is just delta over 6. So that this is truly the edge of the boundary layer, but the boundary layer momentum thickness is 1/6 that high, but they have the same general relationship here, that delta goes as, or theta goes as delta. Well, to plug back into this equation, our wall shear stress to then relate over to here, we need to take the derivative of our boundary layer momentum thickness with x. We find that that is just related to the, it's just 1/6 of the derivative of delta itself, so the actual boundary layer thickness. So now we have this quantity. We can then plug that back into our momentum integral boundary layer equation, and with these two, we can now set up a differential equation for delta itself. And this will then allow us to solve that, applying a boundary condition to solve for delta. So here, on the left-hand side, so now these two are equal to each other, so we have rho u squared over 6. So this comes from our momentum integral boundary layer equation. This comes from the definition of the shear stress at the wall. Separate variables and integrate. So pull all the deltas over here and leave everything else on the right-hand side. We find that this is delta squared over 2, and this one there's no x in here, so it's just, we get an x from integration, plus an integration constant. We know that our boundary layer thickness is 0 at x equals 0 at the front edge of the plate, and so therefore that integration constant goes to 0. And we just get that delta, solving for delta itself, we get the square root of 12 over the Reynolds number as a function of x, right? So this is the Reynolds number, the local Reynolds number, times x itself, right? So that's the boundary layer thickness, and we can see here it goes as the square root of x. And we can then use that to plug back into our relationship for wall shear stress to determine the wall shear stress as a function of x, and we can see that goes as 1 over the square root of x.